Good morning. So, we continue our discussion on recalling some of the embedding theorem and also stating and probably proving some results on inequalities, which will be used for the variation formulation. So, we discussed the embedding theorems in the case of W1P. Now, we will simply quickly state the embedding results for general M and P. Okay. Of course, so you have what happens when M equal to N. So, for m greater than or equal to 1, m equal to 1 we have studied, and p is the growth, okay, p an integer. So, let me quickly state something and then derive something trivial. So, here omega subset of Rn, I will not write it as a theorem, but it is basically a theorem which requires non-trivial proof. Some of them you are already seen it. Okay. Rn B of class, earlier it was C1, so you need more smoothness, Cm. So, the first one is that earlier we have seen 1 less than or equal to P less than N. In this case you P less than N by M. Okay. Then you have WMP of omega embedded in LQ for all Q in P2. We do not call that as P star. P star is precisely reserved for the that embedding. We call it P bar, where P bar is equal to is exactly like the 1 by M n 1 by P 1 by P minus M by N. When m equal to n, it was nothing but P star, and which is nothing but n. So, for all these P you have your embedding thing, sorry, not exactly P bar, this should be 1 by P bar, okay, 1 by P. Okay. And the other case, when P equal to N by M, that is earlier when M was there. So, you will have WMP of omega contained in LQ of omega embedding for all Q in P to infinity, okay, and you do not get it at infinity. And third one, when P greater than N by M, you get a classical smoothness. So, you get WMP of omega contained in L infinity of omega, and in this case, and you also have this one norm t power alpha of u, that is embedding at L infinity is less than or equal to constant into norm u at MP, and you get something extra. Moreover, you get in fact norm of d power alpha of u of x, you get some pointwise Helder type inequality. Okay, d power alpha of u of y is less than or equal to constant into modulus of x minus y power theta. So, let me remove this theta and norm u at WMP of omega. And what is this theta? It is some sort of a, so k is equal to the integer part of m minus n by p, and theta is equal to the integer part, and this is the fractional part m by p. And this is what it says, that this is for mod alpha equal to k. So, you see it is not only that it is in WP is in L infinity, C infinity. So, basically says that, so this implies WMP of omega is embedded in, this implies, that precisely tells you that it implies in Ck of omega bar, and the d power alpha of u with mod alpha is equal to k is an extra inequality. This is something like which you already see, such inequalities you have already seen. This is the case. So, if you have, so in this case look at here. So, if p greater than n by m, so just a small remark. So, p greater than n by m, that is mp greater than n. So, you see m bigger and bigger means that it is the derivative, m derivatives, the more smoothness, and p means the growth. So, you see. So, what it requires is that the product, if you have more and more higher derivatives, that means m is large, you can make mp given p, you can make m large if you have thing more and more derivatives is in w on p this thing. And if given a derivative, if p is also, if the growth is big, still you can make mp greater than 1. So, it plays a role which one depending on your problem you can see which one has more. So, it is a derivative or the growth or both. If that is sufficiently large, it tells you that it will be in some smooth class. That is the kind of thing. So, you can, it plays a role, the m and p. Okay. So, for example, if you have m equal to n equal to 3, m equal to 1, p equal to 2, you get your h1 of omega in 3 dimensions contained up to L6. Okay. For in the other hand n equal to 2, m equal to 1, p equal to 2, you get h1 of omega up to LQ for all q in n to all q in 2 to infinity. You see up to infinity you get it. So, even though you have started with u in L2 and grade u is in L2, that grade u in L2 gives you that it is in LQ. And for if you take, so you can play with it. How? So, according to your problem and the regularities which you do, and you can prove this thing, and p equal to 2, you get your h2 of omega is in contained in C1 of omega bar. So, you see, so you have that kind of result. You have seen that H1 in one dimensional case it is in continuous, absolutely continuous, but H2 that the H1 functions need not be continuous, but if you go to H2 you will get differentiability. So, you can play with it. So, if you this kind of results embeddings are used to prove that weak solutions are classical. Okay. So, you first to prove the, that is a kind of idea. First you prove the solutions in weak solutions in certain spaces, Sobolev spaces, and then prove whether the obtained solution is in a bigger Sobolev space, bigger in the sense that not the largeness of the thing, bigger derivative or bigger growth. Accordingly, you will be able to prove that the obtained solution in Sobolev space become classical, smooth, and you will be able to prove. So, the method of weak solutions also together with the embedding will be able to use to prove the classical solutions. We may see some of them later. Okay. So, with this let me go back to the remarks on Sobolev inequality. This is some remarks on Sobolev inequality, because these things you are already proved thing. So, make it's nice to it leads to some other problems. So, what is Sobolev inequality? For 1 less than or equal to p less than n, norm u at LP star is less than or equal to some constant into norm of grade u at LP, okay, where p star is equal to NP by n minus p. Okay. So, for the I can also use instead of this constant I can put the constant here also. Of course, this if you put it here, see. So, looking for what is the bus constant. Bus constant C bust. Of course, C bust has to be less than or equal to grade U at P by norm U at P star. Okay, that this should hold for all U in W, say 1P of omega. So, C bust for all U in W 1P of omega. These constants are only true in this space, okay, not in W 1P space. Okay. So, let me call this to be S n P omega. So, you call this bus constant. So, you actually, so the bus constant is the smallest of all these possibility, right. So, bus constant here means the best U, the largest U, equivalently the smallest of the right terms. So, it is actually a minimization problem, infimum of U not equal to 0, and you can write it as normalize it, norm U P star equal to 1 is, so you are normalizing how big is the gradient. Gradient of U at P where U is in W 1P naught of omega. That is your bus constant, doing it that way. So, let us start with omega is Rn. Omega equal to Rn. I use a dilation trick. So, I am eventually going to show that the bus constant is independent of omega. Dilation. I can define for U lambda of x is equal to U of lambda x for W 1P of Rn. In Rn means it is the same as W 1P of Rn naught for lambda positive. Then you can compute this. I will leave it as a very simple exercise. It is nothing much to do with it, but you just compute it, your gradient of U lambda at P by this ratio. This ratio is more important. This ratio will give you lambda power minus of 1 plus n over P, P star minus n over P into gradient of U by U. This is in P, P by gradient of U at P star. But you can see by the definition of this 1 plus n by P star minus n over P is equal to 0. So, you can do that. So, this term is not there actually. So, you see this term is 1. So, the ratio of gradient of U lambda, so for any U the ratio does not change, that is what you will get it. So, to use this I immediately prove that the SNP, these are all some interesting results. So, that is what I do. So, consider now this ball omega m is equal to B0 m. Okay. And you, so let me write down your Sm is, as I will write in terms of the square. So, infimum of grade U. So, let us consider in the H1 case, H1 of not of omega. So, you can do it the other case. So, let me do this one, gradient of U at L2, but U not equal to 0, grade norm of U at 2 star is equal to 1. Okay. And let us do this in omega m case. So, this is a decreasing function, you can immediately see that. So, if you have an omega m and you have another omega m2. So, this is your omega m1, and if you have your m2. So, if I take any u in h1 naught of omega 1 omega m1, and then I can extend by 0. This you have seen that if the boundary values are 0, you can get it. You can actually get u tilde is in h1 of omega m2. So, omega m2 is a bigger thing. So, you have every h1 naught of omega m can be considered as a subset of subspace of h1 naught of omega m2 for a bigger omega 2, and you are taking an infimum. So, it decreases. So, Sm is decreasing. Okay. So, that means Sm2 less than or equal to Sm1. But I can do something more using the dilation. So, you can do this is a small exercise if you want. There is nothing using the dilation. I will give you the proof in words, but you write it. Using the dilation, every function in omega m. So, that means if you take a u in h1 naught of omega m1, there exists any lambda. So, small lambda, other lambdas, you can have lambda positive, you can get a u lambda in h1 naught of omega 2, right. You can dilate it. You can omega 2 and vice versa, in the vice versa in the sense that so that is what you can dilate. So, omega 1 function can be dilated to get functions in there, on omega 2 functions can be dilated to get omega m1 functions. So, every function in omega h1 naught of omega 2, there is a function in there, and for which the ratio does not change. From the dilation argument, the ratio does not change. So, the infimum will be the same. So, what I want to show is that the similar thing vice versa as well, and you can show that Sm1 is equal to Sm2. So, every ball your Sobolev constant is the same as far as the ball is concerned. Now, for general omega, so every omega m1, the balls the Sm1, so Sobolev constants are the same. Now, for general bounded omega, what you do is that you can translate. So, you take any general omega in such a way that the center is an interior point. If it is not an interior point, you can translate it. By translating, the corresponding Sobolev constant will not change it. Okay. So, you can always assume, and then you can find balls here and balls here. So, you get it will be squeezed between two balls, and for the balls you already seen that the Sm1 decreasing function, and then you can actually prove that omega the S P n p omega is independent of omega S n p. And there are more results, some more results in this direction. You can actually get some estimates and all that thing. But there is one more result about Aubin and Talenti I want to mention in this one. Result of this requires proof. Okay, results of Aubin Talenti. What they have constructed is that the infimum is in when omega equal to n, omega equal to Rm, the infimum is achieved, only for the function. So, they classify the all the functions where the infimum is only for the functions u of x is equal to epsilon into is constant into 1 plus modulus of x square minus n minus 2 by 2. And for this function u epsilon of x is equal to some constant c epsilon into epsilon plus. So, the entire classification is given minus n minus 2 by 2. Okay. So, for omega equal to Rn, the infimum is achieved only for this function. From here can deduce, again I will change it as a simple thought process. It is not a computation, it is about the thought process. Deduce infimum is not achieved for any other omega. Infimum is not achieved for other omega. The reason is trivial. If you that means you will be working with h1 naught of omega. Suppose the infimum is achieved for h1 naught of omega, then you can extend by 0 and you can see that such functions will achieve the infimum in Rn, but for Rn functions these are the only place the functions for which the infimum is achieved. So, I want to make some more remark, and this also used for later you will see that for example h1 naught of omega is contained in LQ 2 star LQ of omega for all for say 1 less or equal to p, yeah, p is already taken to be 2. Okay, so you think LQ of omega for all q in 2 to 2 star. What is 2 star? Is nothing by 2n by n minus 2. And later so you can actually see that I will make some note about this h1 naught of omega. These are all some compact embedding, which will say you can get a compact embedding in LQ for q in 2 to 2 star open and not compact for q equal to 2 star. So, such things can be proved. So, with this let me go to some remarks on compact embedding and then later we will go to inequalities. Now, compact embedding okay. In general compact embeddings are not true compact. There are special cases you can do it. Embeddings are not true for unbounded domains, true for unbounded domains. For example, whatever be the choice of MP Rn, MP of Rn, which is an unbounded domain, is never compact. There is a very general argument I will tell you now. Never compact in any LQ. You see, LQ of Rn and Rn. So, you there is no this is a very general proof. WMP of Rn, whatever be the higher choice of P and M and whatever be the small choice of Q, it cannot be compact. This is done via a general argument. So, what do you do? You choose balls. So, this is a good argument which can prove not only for Rn, for any other domains, many other unbounded domains. So, choose balls B1, B2, etc. These are disjoint but translation, same type, disjoint but translations of B1. which you can do it in Rn, translations of B1. So what you do is that you have a ball of radius, similar ball, that is what you want. You want a balls, a family of balls with uniform radius from below. So you have the same ball, I do it like this. Okay, so you can start with even B naught if you want, B naught, then translate B1 in a direction. Okay, it does not matter, you want a disjoint poles of the same radius. Okay, that is the thing, same radius whatever it is. That is what I say, if you can have this proof will work if you take any unbounded domain for which you can construct a disjoint family of balls of a uniform radius. Okay. So what you do is that, so you first do, so you call it this to be any BR, so B naught. So you choose phi, so you first choose a phi in domain of R, the compact support R, and then you can normalize it, so that such that norm of phi at WMP of Rn is equal to 1. That is possible, you know, so many functions exist and normalize it, and then you compute it, your norm phi at LQ, whatever be your Q, you call this to be A, and this will be definitely positive. Okay. Now phi j is the translation, so the phi is domain of Rn such that support of phi is in B naught. Now phi j is the translation of phi to Bj, that means the support of Bj is in phi j, support of phi j is contained in Bj. You see, hence this norm of phi j is again equal to 1 WMP equal to 1, and A is also equal to norm of phi j in LQ, which is positive. So this can never be compact, because this is a phi j is a in bounded set in WMP, you see, WMP of R, and but phi j's have disjoint supports, and phi j is not Cauchy in LQ. So it can never converge strongly. So that is what you want, not Cauchy in LQ. Okay. So it is a kind of a general argument, tells you that in general unbounded domains there are some few results I want to again recall, so that you will be immediately comfortable. There is one, though you have studied already, so let me just recall this theorem. I am not going to prove anything. Okay. You have seen already in some form or other. There are many relics lemma, so I do not know. So let K be a compact set. This is one theorem. Let K be a compact set in Rn. Set in Rn. Define H1 So you have an H1k of Rn such that V is in H1 of Rn, then such that the support of V is in K. Okay. Then there is a compact embedding. So full H1 is there, but if you are looking compactly embedded in L2 of Rn. So, that is one theorem, and this theorem can be used to prove immediately. I will give this proof and then stop it, and then we will continue again. There is an immediate corollary is that assume omega is bounded, then one H1 naught of omega is compactly, this is what we will be immediately using for our variational formulation, and H1 also it is true if omega is smooth, omega compactly contained in L2 of omega if omega smooth. Okay. The proof is now immediate. So, let me give the proof based on that. What you do is that there is an extension operator, let P from H1 of omega or H1 naught of omega. If omega is smooth, you have an extension to H1 of Rn, extension. Okay. And now omega is bounded. So, you can omega is bounded, choose a k, compact k is trivial, okay, compact k such that your omega bar is contained in interior of k, contained in k. Okay. So, what you can do from here then, so actually combining these two, you can actually define an operator is, so we can actually, this gives you a combining, you can get a prolongation operator, prolongation q actually from, so q actually from H1 of omega or H1 naught of omega or H1 naught of omega to H1 of Rn k. So, you can define an extension operator in such a way that so it is 0 outside k. So, actually this will get it. So, basically you have an operator q. So, this is your operator q, and then from here to here you have an L2 of Rn. So, this is a restriction operator. So, q is an operator. So, you have an identity, this is an identity operator which is continuous. Okay. And from here, no, here that is so this is the q operator. So, this is a compact operator, this is continuous, and by the previous theorem this is continuous is actually compact. Okay. So, that is what the theorem, by theorem, and then you have a restriction operator. So, you restrict to L2 of omega, restriction, and this is a continuous operator. So, you have from here to here compact. Okay. So, I will state one more theorem in general W1P. In the next class we will in the next lecture we will define one more class, one more theorem, and then we prove some inequalities quickly. Thank you very much.